What if the key to humanity's future in space is a nuclear reactor sitting on the moon? NASA isn't just thinking about rockets, astronauts, and habitats. They're planning on building a 100-kilowatt nuclear fission reactor on the lunar surface by 2030. Why? Because without a reliable power source, a moon base is just science fiction. But this plan isn't science fiction. It's physics. I'm Ben. This is Physics or Bust. Here's the problem. Solar panels work great on Earth, and even on the moon during the lunar days. And lunar days are 14 Earth days long. But so are the lunar nights. That's 2 weeks of darkness at a time. Now things are a little better at the lunar poles, where there's peaks of eternal light, where a vertical solar panel could catch the sun at all times, just rotating around slowly during that month's time. But shadows and terrain still make solar power unreliable. So while a solar panel might be a good supplement on the moon, it can't be the main power source. How about batteries to make it through the night? Not even close. The moon base would need enough batteries to make it through 14 days of darkness. That adds up to hundreds of tons just in batteries. By the time you finish shipping them all there with rockets, you'd need to replace the first ones. So how do you keep life support, communications, science labs, and even some mining equipment running? The answer? Nuclear power. We'll dig into the physics in a minute, but first, if you like this video, you'd probably like this book. I've got a link in the description below. I do get a small commission, but it wouldn't cost you any extra. NASA's design is called Fission Surface Power, and while the name nuclear might sound intimidating, the physics behind it is elegantly simple. At the heart of the reactor is uranium-235, an isotope chosen because its nucleus is relatively easy to split. When a neutron collides with a uranium-235 nucleus, the atom undergoes fission, breaking apart into smaller nuclei and releasing a whole lot of energy in the form of heat, and also releasing more neutrons. The design includes a solid core reactor, not liquid fuels or a complicated high-pressure system. This makes it more rugged for the lunar conditions. Here's where the brilliance comes in. The heat doesn't move through water like in reactors on Earth. Instead, it moves through pipes filled with sodium. Sodium is perfect for this job. It melts at relatively low temperatures, 97.8 degrees Celsius, and conducts heat extremely well. These heat pipes transfer thermal energy to power conversion units. NASA favors Stirling engines, essentially pistons that move back and forth as fluids heat and cool, converting thermal cycles into mechanical energy, and that can be converted into electricity. And finally, large radiator fins release waste heat into space. Because there's no atmosphere on the moon, you can't rely on convection. The only way to dump excess heat is radiation. Glowing infrared panels releasing energy into the void of space. The remarkable thing about this system is that it can run for years with no moving coolant pumps and minimal maintenance. Fewer moving parts means fewer things that can go wrong and break in an environment where fixing things is extremely difficult. This is nuclear power stripped down to its most essential physics. Compact, resilient, perfect for the moon. But making a nuclear reactor work on the moon is a colossal engineering challenge. Astronauts are going to need to be kept from gamma and neutron radiation, so there's going to have to be some kind of shielding protecting them from the reactor. On Earth, reactors are buried in tons of concrete and water shielding. But the amount they would need on the moon would be way too much to launch to the moon, especially since every kilogram costs $2,700, and that's just to get into low Earth orbit, not to mention getting it to the moon. The solution? Use the moon itself. Regolith, the dusty lunar soil, melted and solidified into structures suitable for landing pads, roads, habitats, and even radiation shielding for a nuclear reactor. This work is being done under NASA's Moon to Mars Planetary Autonomous Construction Technologies Project, or IMPACT. Extreme temperatures are another engineering challenge for a base on the moon. The lunar surface swings from positive 120 degrees surface during the day to negative 200 degrees Celsius during the night. Materials are going to expand, contract, and really risk fracturing. The reactor must survive both extremes without failure. By burying parts of it underground and carefully controlling heat flow with radiators, engineers can design it to operate in a much more stable range. Burying parts of it underground has the added benefit of protecting those parts from meteoroid impacts. Unlike Earth, the Moon has no protective atmosphere, so tiny grains of space dust can strike at several kilometers per second. Radiators and heat pipes are going to be especially vulnerable since those can't be buried. One puncture and heat transfer could fail. Engineers are working on redundant designs as well as self-sealing coolant pipes. But before astronauts can bury the nuclear reactor, it first has to launch from Earth. Launching uranium into space can sound terrifying, but there are ways to lower the risks. The main way they'll reduce the risk is by not turning the reactor on until it's safely on the Moon. Since fission needs to be activated for the main radioactivity to occur, the uranium fuel is relatively inert until put into an operating core, reducing the risks during launch. But the fact is, if a launch containing reactor components fails in Earth's atmosphere, even unactivated uranium fuel could spread radioactive contamination. While designs minimize this, public concern is extremely high, as it should be for launching nuclear material into our atmosphere. And every design must withstand catastrophic launch failures without releasing radioactive material. Even so, the risk will never be zero. Even with clever engineering, launching radioactive material into space isn't the only risk and controversy that comes with building a nuclear reactor on the Moon. Radiation leaks are another concern. The Moon has no atmosphere, but astronauts working near the reactor would be in harm's way if shielding failed. Even small neutron leaks can damage human tissue, electronics, and long-term habitats. Political and legal issues will also be a major source of controversy. International treaties like the Outer Space Treaty of 1967 frown on putting nuclear material into space. While power reactors aren't banned, it's definitely politically sensitive, especially if multiple countries are going to start planting nuclear reactors on the Moon. We'll also have to tackle the problem of long-term waste. After years of operation, the spent fuel will still be dangerously radioactive. There's no nuclear waste facility on the Moon, and not much chance of one being there soon enough. The initial solution may be to bury it deep in regolith, but that's a long-term liability for future explorers. Another option some have come up with is to launch the material so that it ends up going into the sun, but that might be trickier than some people initially think. Nuclear power may solve the energy crisis for space exploration, but it also introduces the exact same dangers and debates that we have on Earth, only this time in a place where mistakes are much harder to fix. Nuclear reactors will power lunar mining outposts, fuel processing plants for rocket fuel, and even be needed for trips to Mars. And even beyond exploration, this project will set a precedent. Whoever controls compact, reliable energy production controls the future of space. The Moon is humanity's first step in becoming a spacefaring civilization, but steps need power. And if NASA's plan succeeds, by 2030, we might be the ones to witness the first glow of lights that didn't come from batteries or solar panels, but instead from the glow of a nuclear reactor. So do you think nuclear power is the future of space exploration? If not, what is it? Let me know in the comments below. For more space and science updates, make sure to like and subscribe, and remember, keep asking questions. I'll see you on the next video.